Morning all, and the first lesson of Physics 2, we're going to be concentrating upon forces, which is the major topic within within Physics 2, and getting that done in times to do assessments, etc. And we might do a little bit of waves and magnetism, just so you're aware of it in case you're going on further with your physics, and you've already done Physics 1. So, quick recap from some of the chemistry questions if you want to have a go at those, and then I will fly through the answers after. So pause now. And in terms of answers, you can just mark your own quickly, make a note if you got it wrong. Any corrections for the future would be brilliant. And then on to forces. So don't usually leave these in. Forces can be described as contact or non-contact, and quantities for forces, the size of forces, etc. Quantities can either be scalar or vector quantities, and we're going to come on to doing that. Now, first of all, the first thing that will be in my head is, yeah, but forces is a nice word, but what is a force? And forces can cause things to move. So if an object isn't moving, you'd have to apply a force to make it move. Forces can stop something that is moving. So perhaps a car is rolling, but it's stopped by friction. The force of the car engine can help it move, but the force of the brakes helps it stop. Forces can also push and pull, so forces can change the shape of an object. And then, so force is applied, and when we talk about contact and non-contact forces, if you want to push a shopping trolley, then you hold the handle, your feet push backwards on the floor, and your arms push forward on the trolley. So by pushing backwards, there's a force going forwards. So that is a contact force. A contact force where you have to actually be touching. However, when the needle on a compass points north, nothing's touching it. It's not connected to the north or south pole or the magnetic field, etc. So that would be a good example, magnetism, of a non-contact force. So again, electrostatic forces, where positives and negatives attract each other. They don't have to be in touch to actually attract. So non-contact forces, very much what it says, they don't need to be touching for it to act. And a contact force, it needs to be touching for it to act. So here, obviously, Mr. O'Neill getting a bit out of control in his car on the way to school, sliding down the hill. He does that every day. He just shows off. And as Mr. O'Neill goes along here, he's got a force, obviously, from the car coming down the hill here. And he slides because there's not enough contact with the ground. So contact force is like friction of the tyres. And then unfortunately he hits the curb and he falls out. But like I say, he does that every day on the way to school. He does it show off sometimes. Sometimes he lands on his feet. Whereas over this diagram, what you've got is a spinning top appearing to spin in midair, because it's got magnets in the bottom here that might be north, and you've got other magnets in the bottom here that would be north, and like charges repel with magnets, just like with electricity. So like poles repel with the magnets. So contact forces, where the force applied has to actually be in contact with the object it's doing. When you write out what this means, can you try and give some examples? Like I gave the example, a car needs to be in contact with the road for it to be able to move forwards, because those tyres are pushing off the road to move the car forward. The shopping trolley will not move unless it is pushed by your hands. So in those cases, the pushing, etc., like that, those are contact forces. And non-contact forces, electric static force and magnetism. Okay, so when you've done that, pause for a minute, write out your definitions for those, and then we're ready to move on. That's just defining non is without contact, but we've done that. So from this list over here, stick them into the table. So try and put them into the two groups. So pause, I'll pause while you do that, and then we'll go through them quickly. Okay, so air resistance. Air resistance is where you're rubbing against the air as you move along. You're in touch with the air, it's a contact. And friction. Air resistance is just a type of friction, but friction can be between any objects. And when you rub your hands together, the reason they get hot is because of friction between your hands. Friction on the road with tyres, etc. Grippy trainers for mud. So friction is a contact force. Gravity, non-contact. Objects are drawn towards other objects by gravity. Magnetism, non-contact force. Nuclear force, non-contact. Tension, if we are both pulling on either end of a piece of elastic, the elastic is under tension. If we're both pulling on each end of a piece of wood, the piece of wood is on tension. Maybe it will snap because of the forces, but again, you have to be in contact. Electrical force, the electrostatic force, is a non-contact, and normal force is a contact, and we'll talk more about that in a minute. So Isaac Newton, very, very famous scientist. Most people know Newton's name, and most people link it to an apple. That's not what he did, and that's probably an old wives' tale, because actually he wasn't clever because an apple fell on his head. If you believe that, then you also believe that his name was Isaac Apple Newton, and they named apples after him because his head fell on an apple. So the other thing I said at the start was about scalars and vectors. So when we talk about speed and velocity, so let's just draw a nice little sports car. Obviously I don't expect your artistic abilities to be as good as mine, so don't worry if you can't draw it as well as I can. I might even have tyres on this car. They're a bit worn. Wow. Oh, hold on. While I'm here, a bit of colour in. Might even put some windows in. A little window at the front here. And oh, there we go. Let's have Miss Walker driving the car. There we go. Right. What could we say about the car? We could say about the car, because Miss Walker's a very careful driver. The car is going along at 80 miles per hour. She shouldn't be doing that down the bus lane, but that's just, you know, it's a bit careless, but obviously she wants to get, she's so enthusiastic and wants to get to school quickly. Oh, there she goes, she's happy. The car is moving at 80 miles per hour. That is the car's speed. So, speed is a scalar quantity. Scalar means it has a size. If I said to you that my hand was 15 centimeters long, brilliant, that's a scalar quantity. So scalar quantities are things like, well, we've got here speed, we've got length, mass. I have a mass of 70 kilograms. That is a scalar quantity. It is outside today, it is 5 degrees Celsius. That is a scalar quantity, so temperature. So anything you can measure that has a size is a scalar. So it has a size, an amount, it's a quantity, and that's scalar. So how is that different to a vector? And velocity is a vector. How is that different? Well, a vector has size exactly the same as a scalar, but it also has direction. So now, if I tell you Miss Walker's speed is 80 miles per hour. However, if I tell you Miss Walker's velocity in her beautiful sports car here, her velocity is 80 miles per hour going north. All of a sudden, I've given it a direction. I could have said it's 80 miles per hour going forwards. Again, I've given it a direction. So velocity has a size and a direction, and that's the difference between speed and velocity. Speed tells you the speed it is going at, but velocity tells you the speed and the direction. So it's interesting to know that a meteor is heading at 1 million miles an hour. It's even more interesting to know that it's heading at 1 million miles an hour directly towards the moon. One of those is a speed, one is a velocity, because it gives you the direction. So could you pause and could you make sure that with examples for both, you've got this. If you want another example for vector, like I gave some examples over here for speed, length, mass, temperature, another example for vector would be weight. Your weight is not your mass, and we'll come on to that later in another lesson. Your mass is how many kilograms you are, but your weight depends upon where you are. So weight always acts downwards because of gravity. So weight has a direction. If I tell you my weight is 700 newtons. That means you know that it's 700 newtons pushing down on the earth, or down on whatever I'm standing on. If I'm not on the earth, for example, I might be on the moon. So pause, make sure you've got that really clear in your notes, diagrams, examples, and then unpause, ready to move on. Okay, we've just done that. We've written a definition. So scalar quantities have a size and vector quantities have a size and a... Okay, so with scalar and vector quantities, see, first of all, draw your table out. Here's your table over here. Draw your table out, and then we'll go through the answers. So pause, draw your table out, see which ones you can put in. If you're unsure, maybe do it in pencil, and then we'll move on. Okay, so time. Time has a size, 1 minute, 3 hours, 24 days, has no direction, so it just has a size, it's scalar. Your mass just tells us how many kilograms there are, scalar. Temperature, 15 degrees, just has a size. Speed and direction on its own, direction doesn't have a size. So direction of, oh, I was heading north. If I don't know how much I was moving, if I don't know what size I was moving north, like at 5 miles an hour or anything, direction on its own is just a scalar. Vectors, so all of these things here have a size and a direction. So forces must always work in a direction, and that's why weight is a force caused by gravity. Displacement is probably one that people haven't heard before, so let's just add a little bit of notes about that. Here's your house, I'll label it H, and here is the park where you're going to play with your friends on the swing. And you leave your house and you turn left. Then you take a quick right. You have to go down here, round the roundabout, down this road, and then there's a cut through here to get to the park there. That red line I've just drawn all the way along here is called the distance. However, the displacement, you have actually just physically moved from here to here, so in a straight line. That is your displacement. Displacement gives us a direction that you've moved overall, and it gives us how far you've moved, how many meters. So displacement in meters, obviously if you live in a straight line from somewhere, the distance and the displacement would be the same. But roads aren't like that, paths aren't like that, unfortunately, unless you go next door. So velocity, that shouldn't be there. It should be meters per second. Get rid of that too. That's a mistake somebody's put in. Acceleration, an increase in speed, has a direction. And momentum, some might be thinking, what's momentum? Well, if you've got an empty shopping trolley, hold on, oh, a bit more artistic skill. There we go. There's your shopping trolley. If you have an empty trolley, it's easy to start it and it's easy to stop it. and you know that, and you can take corners quite easily. If you have, and you've all done this, you've probably all been dragged around a supermarket pre-COVID with your parents, and you've been pushing the trolley, and it's absolutely chocker, full of stuff, loads of tins of really nice things like corned beef and tuna, a couple of bananas, not tins. That trolley now is hard to get moving, and when you get to almost hitting somebody, it's hard to stop. You need a much bigger force. That's because that trolley's got more momentum. So momentum is affected by your speed and your size. It's much harder for a lorry or a train to stop than it is for a small car. That's why bikes can brake quickly, but cars can't. So momentum is that movement force because of your size and speed. Lots of car crashes are caused not because people didn't see things, but the car or the van or the lorry have got too much momentum to stop in time. Okay. Now, arrows. Forces, remember, are all vectors. And that means because they have a size and they have a direction, that means that a vector, like a force, can be shown in a diagram. And this is an example of that. Here is a rocket, and look at the two arrows. This arrow at the top here is much, much bigger. So we draw them to scale as much as possible. And this is showing that there's two forces acting upon this amazing spaceship. This is Mr. Phillips's spaceship, and this is how he travels home to Venus every evening, because obviously you know that Mr. Phillips is an alien. Now, why is the rocket flying up? Well, it's flying up because this force here is much bigger than this force here. This arrow going up is much bigger than this arrow going down. So throughout forces, we'll use arrows to show directions and to show size. It's showing the force, size and direction. Let's go back to Miss Walker's car. Boom, boom, boom. She obviously like give it a bit of a smash, which is why it's changed shape. Miss Walker's car here. If I drew this on it, or if I drew this on it, that one would be showing that there's a much bigger force going forwards than this little force here. So we can interpret that as that's a much faster force. If we then drew the friction on it, that force is acting against it from the wind and the road, we could say, the bigger force, okay, she must be accelerating, she's getting faster and faster. We'll do some more arrow diagrams, so don't worry about that. And this now is for higher tier. So it's very easy sometimes when you've got the rocket force and the rocket was going this way and the weight was going this way, and you just take one away from the other, and it's obvious that overall it goes this way a bit. It goes up. The issue comes when here is a boat looking at it from above. And here's the cabin where the captain is sitting having his rum. And here's some cargo they're carrying, and it's going along, and it's a big heavy boat, and there is a force acting this way from the engine. There is also the wind coming from this direction, and it's a very strong wind. So think to yourself first of all, before I go through it, what will now happen to that boat? It's obviously not going to move backwards. It's not going to start spinning in circles. That boat wants to head for here. There you go, there's the port. At the moment though, what's going to happen to that boat? And the answer is, well, there's a force acting here and there's a force acting here. Both forces will have an effect, and actually it will end up going, this force is bigger, so it will go more forwards, but it will go down a bit and it would miss the port perhaps. So maybe what they need to be doing is changing and aiming here so they end up going that way. So actually, how do we get this overall force? And that's called a vector diagram. So put a mini title, vector diagrams, and we'll try a couple of these together. So in our question here, a force is applied on an object with 5 newtons of force, and another force of 3 newtons is applied at 30 degrees. So what we do is, all you have to do, and you'll be given squared paper or you'll be given graph paper on an exam paper to do this, and you just use a ruler to draw a scale diagram. On here, for example, we've decided on a scale, because it's squared paper, of 1 Newton per centimetre. So all I'm going to do is I'm going to go, here's my object, and my object, I need to make my pen thicker. Oh no, I'll change colour, that's easier. Right, here I go 5 newtons this way. 1, 2, 3, 4, 5 newtons this way. Then I get my compass out and I measure 30 degrees from that direction, and this force is applied, and this is 3 newtons, so I go along and I measure 3 centimeters. So I go 1, 2, 3, and now I've got my 2 forces. So where do I end up? And what you do is you just have to complete the trapezius. That sounds easy, especially if you know what a trapezius is. So what you do next is you complete that. So at 30 degrees here, you draw another 3 centimeters, and then you draw your 5 centimeters. So these are just planning lines. And now I've got this. It's not a rectangle, it's not even a square. That's why it's called a trapezius. And then this corner to corner is my force. That's what's actually happening. So if this was a boat with 5 newtons going that way and 3 going this way, this blue line in the center that I've just put a circle on is that's the resultant force. And all you do then is you get a ruler, you measure it, and maybe that comes out at 7.5 centimeters, so 7.5 newtons. So those 2 forces, sort of in the same direction but not directly. It's much easier when they say Johnny is going along on his skateboard with a force of 4 newtons and his friend gives him a push of 3 newtons. If they're both in the same direction, that just equals 7 newtons going forward. That's the resultant force. So could you copy this example out, and could you explain that the resultant force is, when you look at all the different forces acting, the resultant force is the force that acts overall. Okay. This is just exactly the same. Oh, look at that. I guessed it right. It was 7.5 newtons. It's almost like I know what I'm talking about sometimes. Different example. Pause on it. Maybe use it as a second example in your notes. And now you have a go. So you try this one. So you have to work out a scale. Now, space-wise on here, maybe you're doing, I know what I could do. I could do a scale. I've got to fit 200 newtons onto here, so maybe what I do is 1 centimetre equals 20 newtons. There you go. That's all I'm helping you with. So complete that. And here are some exam style questions. So, worth you trying. Sending your work to your teacher, letting them check if you understand it or not, and obviously then we can move forwards with it. Exactly the same. Exam questions. This one here, remember? Momentum. Yeah, no, that will add direction because it was the size and the mass. So ticking those.